and get started. And another video that begins with the word okay. Oh well, I've come to accept it now. So we're going to talk about balancing redox equations, and there's one major difference when you're balancing an oxidation-reduction reaction as opposed to just a normal reaction. You need to pay attention to two things. Before, we've only paid attention to mass, making sure, not mass, but the number of atoms on each side, making sure that they are balanced, okay? Or I guess law of conservation of mass as well, because if you have the same number of atoms, you're going to have the same mass on both sides. But usually what we're paying attention to is the number of atoms when we balance. With a redox, the charges are changing sometimes on particular atoms or ions. And so we have to make sure that the electron flow is also balanced here, okay? And there are actually scenarios where you might balance the atoms correctly, but you do not have the charge balanced correctly. All right, so you have to watch out for that. There's kind of two things you have to pay attention to now. But before we start talking about the method that we're going to use for this, and there's a very systematic method to this, and I think you guys are going to pick up on it as soon as I teach it to you. And it'll be fine, but we need to talk about half reactions first, okay? Now remember, we talked about this, hopefully you guys got a chance to watch the video last night. It was only 15 minutes, if you didn't get a chance to watch it, and it's basically just a review of some stuff that we had talked about before, so hopefully it was just a little bit of a refresher, and it was like, oh yeah, I remember all of this. But oxidation and reduction always happen at the same time, all right? Because oxidation, what happens in oxidation? You lose electrons, right? That's Leo, okay? So if electrons get lost by one thing, then they have to go somewhere, all right? So something else is going to gain those electrons and be reduced, okay? So you can't have one without the other in an oxidation-reduction reaction, all right? It has to be both. So the equation here, you've got SN2 plus 2 Fe3 plus yields SN4 plus 2 Fe2 plus. Now again, just looking at this initially, it sort of seems like that 2 doesn't need to be there, right? Because if we're just thinking about the number of atoms here, why do we need a 2 in front of the Fe here and a 2 in front of the Fe here? That's not necessary, right? But if you're looking at charge, it is, okay? Because there's a 2 plus here and a 3 plus here, so that would add up to 5 plus. If we didn't have a coefficient here, then the 4 plus on the 10 plus the 2 plus on the Fe would add up to 6 plus, okay? So our charge is not conserved at that point, all right? But if you put the 2 there in front of both of those, then that should work out. Now you've got an 8 plus on this side and an 8 plus on this side, okay? Kind of see how that works? Okay, you have to make sure that the atoms and the charge are balanced. So sometimes you'll have to put coefficients in front of things and it doesn't really seem like maybe they need to be there at first glance. Okay, but the point here that I was trying to make on this is the SN2 plus gets oxidized, the Fe3 plus gets reduced. Okay, but it's going to be helpful for us while we're balancing these to actually split these processes up. Processes, is that right? Yeah. Processi? That's not right. Okay, so anyway, we're going to split the processes up, and we're going to write the oxidation reaction here and the reduction reaction, okay, as though they're kind of two separate things happening. Now, both of these really are happening at the same time, but we're going to split them up and deal with each of them separately. So the oxidation reaction that's taking place, the 10 is becoming more positive, right, which means it's losing 2 electrons. Does that make sense? Okay, so if we write the oxidation half reaction here, we're going to write SN2 plus yields SN4 plus 2 electrons. Okay, and then on the reduction side, we've got this 2 Fe3 plus 2 electrons. So that's gaining those 2 electrons, right? And then you end up with 2 Fe's that have a 2 plus charge. And again, you just kind of have to notice there, the reason that we need 2 electrons, 1 electron goes to each of the Fe3 pluses, okay? And then we end up with 2 that have a 2 plus charge. All right, so that's kind of how that works. Half reaction basically shows the oxidation reduction by itself, and the number of electrons lost in the oxidation has to equal the number gained in the reduction. Okay, and that is the key here, really, to balancing these things. You have to remember, in other words, if I have 2 electrons being lost here, then I need to have 2 electrons being gained in the reduction half reaction. Okay. All right, so let's talk about how to balance these things. Right. A lot of times, I would say most of the time, they're going to tell you that these things are happening in acidic solution or in basic solution. Okay. A lot of times, redox reactions won't occur unless they have that H plus available to them. Okay, and so we're going to assume, I should have written it on here as part of the problem, but we're going to assume that this is taking place in an acidic solution. Okay, because we need something that's in the acidic solution in order to make this equation actually work. Right, so this is an example of an unbalanced redox reaction. Okay, now if you just count the number of atoms, I'm not sure if it's... No, it's not balanced already, right? You can see that this is unbalanced just by counting the number of atoms. We have the same number of manganese, but we do not have the same number of oxygen on each side. We've got 8 on one side, 2 on the other, and then the carbons are not balanced either, okay? So first thing we want to do is we want to write the 2 half reactions here, okay? In order to write the 2 half reactions, we're going to have to figure out well, see, I was going to say we have to figure out what the oxidation numbers on all these things are. You could do it that way. Yeah, let's do it that way to start out with. Okay, so, and then I'm going to show you kind of a little bit of a shortcut here that might make these a little bit faster. Usually you can identify which 2 of these are going to go together in a reaction. Can you just take a guess by looking at it? What 2 things maybe go together in our first reaction? In other words, if I'm splitting this apart into 2 different processes, then the MnO4 minus, what might that change into that we would want to pay attention to? Maybe the Mn, okay, because that's the manganese is probably the thing changing oxidation number here, okay, or one of the things. Now, we're just guessing at this point, okay, and we'll find the oxidation numbers of all of these to verify that. But I'm just trying to show you sometimes you can take a little bit of a shortcut here. And then probably the carbon is the other thing changing oxidation number. Again, if you don't see that right off the bat, that's okay. I'm just remembering my rules here, and I'm remembering that oxygen is usually a 2- when it's in a compound. Okay, you guys remember that? The exceptions to that are when it's with peroxide. There is no peroxide here, okay? Or when it's by itself, right? Then it would have an oxidation number of 0, right? Because if it's O2, it would just be a 0 oxidation number. And I don't see that situation for the oxygen anywhere here, okay? So probably it's the manganese and the carbon that are going to be changing oxidation states. All right, but we'll go ahead and check it just to make sure. The oxidation state on the oxygen here is, here I'll put the charge, or the oxidation state for each individual oxygen at the bottom, and then I'll put the overall oxidation state on the top. I think that's the way we did it earlier in the year. So the oxygen has a 2- oxidation state, but there are 4 of them. So overall, that's an oxidation state of, or an oxidation number of 8-. Okay. And now overall, this is a 1- charge. So what does the charge on the oxidation state, I should say, on the manganese need to be? This is weird. It's +7. Okay. Yeah, now we're getting back into the world of oxidation numbers. And you got to remember, an oxidation number is not the same thing as a charge. Okay? So you just got to keep that in mind. This is actually a polyatomic ion, the MnO4-. Okay, so this is actually covalently bonded. I know it's a metal and a non-metal, and that's a little weird. Okay, but it is covalently bonded. So, C2O4 2-. Once again, the oxygen here is going to be a 2-. and an 8 minus overall, right? So now we got to do a little more thinking here. In order to end up with a 2 minus overall charge, then the carbons need to be, right, they need to be 6 plus overall, right, which means each carbon needs to be a 3 plus. Okay? Now on the second side, we can clearly see here the manganese is a 2 plus charge, and when you have something that's charged, then its charge equals its oxidation number. Okay? So this is going to be a 2 plus. And now I'm running into my top thing here. Can we just sort of look at this and figure out what the oxidation number on the carbon is going to be here? What's it going to be? Is everyone in agreement with that? There's 2 oxygens, each with a 2 minus charge. So the carbon's going to have a 4 plus here. Okay. So we were right. It looks like the manganese and the carbon are the 2 things that are changing oxidation number in the course of this reaction. Right? So what I'm going to do is I'm going to write the 2 half reactions here. And again, I'll label it this time. You don't have to label these as oxidation or reduction. You're going to be able to see it eventually anyway. But for right now, which one is our oxidation half reaction? Or another way to say that, what is being oxidized here? The carbon is being oxidized, okay? So the carbon is starting out as 3 plus going to a 4 plus, so it is losing electrons, all right? So the way we're going to write this, it's going to be, and leave yourself some room here, because we may have to add things to both sides of this. C2O42 minus yields CO2. And these are both aqueous. I guess I could label that. I'm going to be a little lazy here. And then our reduction half reaction is going to be probably the other one. MnO4 minus yields Mn2 plus. Okay? So that's step 1, is that we just write the 2 half reactions. And again, you don't have to know which one is oxidation and which one is reduction at first. So you can kind of just keep the same species together, and then you don't really have to worry about the oxidation state so much. Now, if you want to be really careful and make sure you're doing this right, you might label the oxidation state on all these. Okay. In an acidic solution, we've got some other things available to us to help us balance this thing. We've actually got H plus ions, and we've got H2O. Okay, so that can actually help to balance this equation. In fact, this reaction wouldn't occur unless there was H plus and H2O available to it. Okay, because otherwise it couldn't really work. So we want to balance the permanganate half reaction. You guys know which one is the permanganate? MnO4 minus is the permanganate, all right? So this is kind of low down on the screen. I apologize for that. But the MnO4 minus going to Mn2 plus. The first thing that we want to do is we want to, oh, wait a second, do I have it step by step here? No, I guess I don't. Okay. All right, so the MnO4 minus goes to Mn2 plus. There's something kind of strange about that reaction to begin with. We don't have any oxygen on the right side of that equation, right? Okay, it's not the H plus that's going to help us there, right? What else do we have available to us in that solution? H2O, that has oxygen in it, right? Okay, so it's actually, the water is actually going to participate in this chemical reaction, okay? Now, let me say this first. One thing that we should look for at the very beginning is to make sure that our other atom is balanced. We have 1 manganese on the left side, 1 manganese on the right. Okay, so we're good there. Sometimes you might have to put a number in front of one or the other of those to balance out the atom that's actually being oxidized or reduced. Okay, but because we're good there, let's just go ahead and add H2O to this side. Now, how many H2O atoms or molecules do we need to add? We need 4 oxygens, so we need to add 4 water molecules, right? 4 H2O. Well, now we just totally screwed things up because there's no hydrogen on the left side of this thing, right? but we also have H plus available in this solution, okay? Now, how many H pluses do we need to add to the left side? 8, okay? All right, so now our atoms are all balanced, and we're okay there. But our charge is not. Can you guys see that the charge is kind of off here? All right, what's the overall charge on the left side of this equation? 7 plus, right? So there's a 7 plus over here. What's the overall charge on the right side? 2 plus, okay? Now, the charges don't have to be equal to 0, but they have to be equal to one another, okay? So what might I add to the left side of this equation that would help my charges balance? This is where it gets tricky. Something that maybe has a negative charge, perhaps. Good thought, but this is an acidic solution, so we don't have any OH minus available to us. She didn't like this. Okay, let me just help you out with this one. We're gonna add electrons, okay? And we're not adding electrons. I mean, there's actually electrons being transferred here, right? So how many electrons do I need on this side in order to balance this thing? 5, right? Okay? So there is our half reaction, and that's our reduction half reaction, okay? And that kind of makes sense. Look at where the electrons are. They're on the reactant side, right? So they are reacting with the MnO4 minus to make the Mn2 plus. So it's gaining electrons in this process, okay? So in a reduction reaction, the electrons are going to be on the left side of the reaction. All right? Now, oh, whoops, that's where that was supposed to be, sorry. Where it says how to balance the charge on the permanganate half reaction, I guess just for the sake of doing this correctly, because we're going to need it on the next screen anyway. So 5 electrons, 8 H pluses. MnO4 minus. Mn2 plus, 4 H2O. Okay, and again, I would just check at the end to make sure everything's balanced. We know the charges are balanced. We were just paying attention to that. The manganese are balanced. The oxygens are balanced. The hydrogens are balanced. So everything looks good. Balancing the oxalate half reaction now, we've got to do something else here. Okay, so C2O4 2 minus going to, isn't it CO2? Is that right? Okay. So this right here, we decided it was our oxidation reaction. That doesn't really matter for the time being, okay? But the first thing we have to do here is make sure that our carbon is balanced, okay? Which it is not. So let's put a 2 in front of the CO2. Interesting. That's a little bit easier, isn't it? So we're balanced, right? No. Okay. The only problem here is the charge is not balanced, right? The number of atoms are balanced, so we don't have to worry about adding H2O or H plus or anything weird on this one, okay? The atoms actually balance out the way that they are, but we do need 2 electrons on the right side of this equation. Okay? Well, that doesn't work out so well, because evidently this part of the reaction is gaining 5 electrons. This part of the reaction is only giving away 2. Yeah. So, any ideas what we might do next? That's sort of what we do, okay? Now what we need to do is kind of keep this whole thing balanced, right? If we just add more of the C2O4, that's going to throw off the balance of this reaction right here. But what we need to make sure of here, and let me see, okay, getting the number of electrons equal in both half reactions. So let me rewrite this here. 5 electrons, 8H plus. I have a horrible memory. MnO4 minus yields Mn2 plus, plus, I think it's 4H2O. and C2O42 minus, oops, two CO2 plus 2 electrons. Okay, what we're going to do here, and this is the key, okay, and I said it before, the number of electrons gained in the reduction needs to equal the number of electrons lost in the oxidation. So the key to all of this is the electrons, okay? We need to have the same number of electrons in both half reactions. Well, how are we going to get that? This is 5 and this is 2. Yeah, except let's not start multiplying by numbers that aren't whole, because that gets a little weird when we're balancing it. But but we can do something very similar to that, actually. What if I multiply this whole equation by 5, and I multiply this whole equation by 2? Okay? So that should get us 10 electrons on each side. So now, if I rewrite this whole thing, and I add it all together, so I put everything that's on the reactant side together on the reactant side, and I put everything that's on the product side together on the product side. This is going to get a little bulky here, so save yourself a lot of room. So 10 electrons plus 16 H pluses plus 2 MnO4 minus plus 5 C2O42 minus yields 2 Mn2 plus 8 H2O plus 10 CO2, I'm going to run out of room, plus 10 electrons. Okay? And now we can cancel out anything that's on both sides of this equation. The only thing that is the electrons, right? So in a finished, balanced redox equation, you're never going to see the number of electrons because they should always cancel out. The number of electrons on the left side should equal the number of electrons on the right side. Okay? So just cross that out. Cross that out. And there is our balanced chemical equation. No problem, right? Yeah. But it would be very hard to balance that without using that process. Okay? So you kind of have to use that process in order to be able to do this well. Okay? Alright, so here's the summary for what we just did. Hang on, let me pause it for just a second here. Okay. So again, the rules for what we just did, okay, so we kind of just did it, and now I'm telling you the rules because I actually think that sometimes works better if you do it first, and then you're like, oh, okay, so this is what we do every time. You're going to divide the equation into 2 incomplete half reactions. One's going to be oxidation, and one's going to be reduction. Like I said, you don't always have to know that if you kind of get a sense for how these work. You can figure it out once you balance each half reaction, okay? Then you're going to balance them. You're going to balance the elements other than hydrogen and oxygen first, okay? And then you're going to balance the oxygen atoms by adding H2O to one of the sides of the equation. You're going to balance the hydrogen atoms by adding H plus to the other side. And then you're going to balance the charge by adding electrons to the side that has the greatest overall charge, okay? Then you'll multiply each half reaction by a whole number, so that the number of electrons lost in one half reaction equals the number of electrons gained in the other. Then you're going to add them together. And simplify when possible. Usually the only simplification you're going to do is just canceling out the electrons. Okay? And then you're going to check the equation at the end to make sure that everything's balanced. Now that's the one thing we did not do over here. Whoops, it went away. I'm going to let you check that on your own paper. Okay? Yeah. Okay, let's try another one here. Complete and balance the following equation by the method of half reactions. So, can you kind of tell which 2 half reactions are going to go together here? The CR is probably going to go with the CR, right? You guys see that? Okay. So let's not worry about the whole oxidation reduction, figuring out the oxidation number thing here. I'm trying to save you a little bit of time on these because they do take a long time. Okay? So I'm just going to write the 2 half reactions here. CR2O7 2 minus yields CR3 Cr3 plus. And then my other half reaction is going to be Cl minus yields Cl2. I guess I should label that as a gas, because not that it matters here, because we're just going to follow the balancing procedure. You don't really need to worry about oxidation number. But those are our two half reactions, okay? So first thing we need to do on the top one is what? Okay, not yet. Not the H2O yet. Good, to put a 2 in front of the Cr, because there's 2 chromiums on the left side, right? So we need 2 on the right side. Got to be careful with that. If you forget to do that at the beginning, what that's going to do is it's going to mess up your charge. So when you're counting up your charge at the end, you're going to add the wrong number of electrons, okay? So you got to be careful with that. Now we can do what you were just saying. We can add the water, okay? So we're going to add the water to this side because we need 7 oxygens on the right side. So we're going to add 7 H2O, which, again, introduce some hydrogen into this equation. So we're going to add 14 H pluses on the other side. Okay. So then we need to think about our overall charge here. On the left side, our overall charge is what? 12 plus, right? Because that whole Cr2O7 is a 2 minus charge. And then what's our overall charge on the right side? 6 plus. Now again, if you hadn't put the 2 in front of the Cr, if you forgot about that part, you would have put a 3 plus there, right? Which is going to mess up the number of electrons that you add. So where are we adding electrons and how many? We need to reduce the charge on the left, right? So we're going to add 6 to the left. Hit the tab thing. Sorry, I'm running out of room here. So 6 electrons on the left side. So now we know what type of process is happening here. Is this oxidation or reduction? This is reduction, okay, because we're adding the electrons to the Cr2O7 to make the Cr3 plus, okay? Then we need to balance the other one. This one will be a little bit easier because there's no oxygen there. Just put a 2 in front of the Cl, okay? Now I just need to balance my charge. Okay, so this is a 2 minus, so we could add H pluses, but then we got a problem with, you know, hydrogens and everything like that. So let's just add 2 electrons to this side, right? Okay, so this is the oxidation process, okay? These chlorines are being oxidized, and so they're giving away 2 electrons. Now this process that we have written, giving away 2 electrons, but this top process needs 6. Multiply the bottom one by 3. Okay? And then we just add it all together. See, this isn't so bad once you start getting the hang of it, right? If you know the electrons are going to be canceled out, you don't need to write the electrons in, and then, yeah, that'll save you a little bit of a step. Because there's going to be 6 on the left, 6 on the right, okay? So we've got 14 H pluses here, plus Cr2O7, 2 minus, plus 6 Cl minus, yields 2 Cr3 plus 7 H2O, plus 3 Cl2. Okay, and I am being a bit lazy here. I probably should put all my states of matter in. I'll just put this one as a gas because that's the. I'm not going to on the rest of them. I mean, the H2O we can assume is a liquid here. Everything else that has a charge is aqueous. I don't think you really have to label your states of. Well, I know you don't have to label your states of matter on the AP exam. Okay, so I just put that one in because it's different. But then you would go back and you would check all of this to make sure we've got it right. We do. It's right. Okay. You can check it if you want to. It's all there. Okay. So now we need to talk about how to do this in a basic solution. All right. So let me take a break for just a second here. Okay. So here's the thing. These reactions can sometimes occur in basic solutions as well. Okay. Now the problem with the basic solution is we don't have H plus in a basic solution, we've got additional OH minus, right? And it's more difficult to balance the half reactions with OH minus and H2O because they both have oxygen in them. Okay, so adding OH minus to one side is going to throw off your oxygen and your hydrogen, just like the H2O does. So we're going to cheat a little bit here, okay? So I'll show you how to cheat. We're going to balance the half reactions just like we were doing. We're going to pretend it's in an acidic solution, and then we'll go back and we'll fix it at the end, okay? It's much easier, I think, to do it that way. And I'll show you what this little part at the bottom explains what we're going to do, but it'll make more sense once we actually do it, okay? All right, so let's look at this one. Now, you do have to pay attention to this because sometimes they will say this is occurring in an acidic solution. Sometimes they'll say this is occurring in a basic solution. You really have to pay attention to that because you are going to have to fix something at the end if it's in a basic solution. All right, can we identify our two half reactions here? Cn minus going to CnO minus, right? And then the other half reaction is going to be the MnO4 minus going to MnO2. Solid. Okay. So again, we're going to use the exact same process. The only thing that's different is something that we do at the very end. Okay? So the Cn minus, CnO minus, what would we need to do to start balancing this one? Okay, we're going to add H2O to which side? To the left side. We've got an extra oxygen over on the right side, so we're going to add an H2O over here. Okay? Well, now we threw off our hydrogens, so we... Right. So we add H plus, okay? Now this is not, I just want to be clear, this is not what's happening in this solution right now, okay? We're just pretending that it is, okay? But if I added 2 OH minus over here, now our oxygens are off, so now we've got to keep going back and forth, and that just gets tricky, all right? This is easier. So now we need to think about our charge, because I think we've got all of our atoms balanced at this point. This is overall a 1 minus over here. Over on this side, this is a 1 plus, right? Now, just general rule of thumb. I don't want to say that this always holds true, but typically the side that has the H plus on it is the side that you're going to put the electrons on, okay? But again, I would just work out the charge, okay? But that's just a general rule of thumb that typically works. So how many electrons? 2 electrons on the right side, right? And that's going to get both sides to a 1 minus charge, okay? Now, the bottom one here, MnO4 minus to MnO2, unfortunately on this one we've got to do some of the same H2O, H plus stuff that we did on the top one. Add 2 H2O to the right side. Not H2O2, H2O. Okay? And then we need to add some hydrogens to the left side. How many? 4. Okay, so then our overall charge on this side is going to be a 3 plus. Just stop me if you're not following on this, okay? And then our overall charge over here is 0. So how many electrons on the left side? 3. And this is unfortunately another one of those where we have to multiply both equations by something because this is an even and an odd number. Yep. So multiply the bottom one. I don't know why I keep starting with the bottom one. Multiply that one by 2. Multiply the top one by 3. And then we'll add these together. Try to leave yourself some room because there's one more thing we have to do here. And this just gets nuts. Yeah, I know. So 3H2O. I'm going to write really small. 3H2O plus 3Cn minus plus, and we can leave out the electrons, all right, because we've got 6 in both reactions here. They're going to cancel out anyway. Plus 8H plus 2 MnO4 minus yields 3 CnO minus plus 6H plus Okay, that's the electrons. So then down here, 2 MnO2 plus 4 H2O. Okay, now in this particular instance, we do have some things we can cross out on both sides of this thing, right? So just for the sake of space, I'm going to do some erasing here, but this 6H plus on this side cancels out with the 8H plus over here, right? So the net equation here is that we have 2 H pluses on the left side. Does everybody see that? Okay, because 6 of those will cancel. So I'm just going to erase this, and then I'm going to change this to a 2. We can also do that with the water, right? Because there's 3 H2Os on the left side and 4 on the right side. So I'm just going to erase the 3 that are over here, and then erase the 4 that's in front of that H2O. All right? So there's our net equation. But the problem with this net equation that we have written is it has H plus in it. And we know there's no H plus in this solution, there's OH minus, because this is a basic solution, okay? So here's what I'm going to do. I'm going to add OH minus to both sides of this equation, okay? And this is weird, but this is like in algebra. When you add something to both sides of the equation, it doesn't really change the value of the equation at all, okay? So that's kind of what we're doing here. So what I need to do is add as many OH minuses as necessary to cancel out the H plus, okay? So I've got 2 H pluses written on this side right now. I'm going to put 2 OH minuses on this side, okay? And then I'm also, so that I don't change the value of the equation here, I'm going to put 2 OH minuses on this side. Now, when OH minus and H plus react, what happens? They form water, okay? So now, and again, we got to do a little more addition here to simplify this thing. Now I have 2 H2Os on this side. I told you this one was crazy. Plus 3 Cn minus plus 2 MnO4 minus yields 3 CnO minus plus 2 MnO2 plus H2O plus 2 OH minus. Okay? One more step. Does anybody see it? Okay, now I have water on both sides of the equation again, okay? So I'm going to cancel out this water right here, and I'm just going to get rid of the coefficient in front of that water, okay? There is your final balanced equation, and I feel better about that because we have OH minus in that solution instead of H plus, okay? Does everyone understand the correction we made at the end there? Okay, so we just sort of cheated a little bit. You can do this with OH minus and H2O, it's just a lot harder. So I think this is a much easier way to do it, which says a lot because that's not an easy way to do it, right? So, okay, so that's, you just got to pay attention to whether it's in acidic or basic solutions. I would say the vast majority of the time on the AP exam, you're going to be an acidic solution, okay? Yeah, the vast majority of the time. All right. So, another kind of problem that you might get on the AP exam is a question like this, and this might come especially like on the multiple choice section. How many electrons are transferred in this reaction, okay? And so, the problem here is you can't just look at this thing and know right off the bat because the electrons have already canceled out, right? Does anybody have a sense of maybe how many electrons have been transferred in this reaction? This is kind of tough. Here's what I'm noticing. There are two half reactions here, right? There's the MnO4 minus and the Mn2 plus half reaction. And there's the CH3OH and the HCO2H reaction. You guys see that? And then the H pluses and the H2Os are in there because we were adding those as we're balancing the equation, right? Okay? What do you notice about the coefficients in front of both of those? Well, they are large, but it looks like maybe we multiplied one of the half reactions by 4 and the other one by 5. You see that? Now, I mean, we can work this out, okay? And I probably will just show it to you. But if I multiplied one of these by 4 and the other one by 5, then probably I had 4 electrons in one and 5 electrons in the other, because that's going to get me to 20. Does that make sense? So probably there were 20 electrons transferred here. All right, but let me kind of back up. That's the really fast way to do this, okay? But it's also the way that's the easiest to mess up if you're not careful, okay? Here's what I would do. I would pretend that we're starting over with this thing, okay? And at the beginning of this reaction, unbalanced, this is probably what it would have looked like. MnO4 minus plus CH3OH yields Mn2 plus HCO2H. Okay? That's probably, if they had just given you an equation to balance, that's probably how they would have written the skeleton equation for that one. Okay? Do you guys see that? All I did was I took out the H plus and the H2O, because that gets added later while you're balancing the equation. Okay? So then I'll just write my two half reactions here. I've got MnO4 minus yields Mn2 plus, and I've got CH3OH yields HCO2H. Okay? And then I'll just balance this thing the way that I have been before. Okay? Now we don't have to finish this one. All we need to do is know how many electrons total are being transferred between the two. All right? So I'm going to add 4 H2O to this side, and then I'm going to add 8 H plus to this side. Okay? And that's going to leave me needing 5 electrons over here. Actually, we already did this half reaction, didn't we? Earlier in the notes. Okay. So is everybody following me so far on that half reaction? And then this half reaction down here, looks like the only thing that's really off here is my oxygens, right? You know, and my hydrogens. Right, so we're going to add H2O to the left side because we need one more oxygen here. And actually, that takes care of my hydrogens, doesn't it? No, that makes it worse, sorry. Okay, so now we've got 6 hydrogens on the left and 2 on the right, so we need to add 4 H pluses over here. Which, that makes sense, otherwise we don't have a charge on either side. So then, just like I said, we have to add 4 electrons to this side to balance out the charge, right? So now we've got a 4 electron, 5 electron situation here. We're going to multiply this one by 5, we're going to multiply this one by 4, and that's going to give us in our final equation 20 electrons on each side. Does that make sense? So the answer here is 20 electrons are being transferred. Okay? And again, if you can just kind of in your mind figure out what the two half reactions are, a lot of times they're going to have the same coefficient. You can tell what we had to multiply these two things by, and then you can figure out the number of electrons. But that's a lot of mental leaps, so you might be better off just going back to the skeleton equations here and start over with your half reactions. Does that make sense? Okay. Magnesium metal is added to a solution of hydrochloric acid. Write the balanced chemical equation for this reaction, then write the oxidation-reduction half reactions. So this one won't take us very long. This is something that you would often see maybe on number 4 on the short answer or the free response section, which is the equation writing question. So this might be part 1, right? Write the balanced chemical equation. And then for the second part, they always ask you some sort of question about the reactions. And this is a question that they'll ask often, like write the oxidation half reaction or write the reduction half reaction. Okay? So magnesium metal is added to a solution of hydrochloric acid. Mg plus HCl. What's going to happen here? Okay. MgCl, I'll go with that, except for we got to get the charges right and our subscripts right. Okay? What's that going to be? What charge does Mg have when it forms an ionic compound? 2+. The chlorine's going to be 1 minus, so it's going to be MgCl2, right? Okay, plus, this is basically a single replacement reaction. Remember those? Okay, so then the hydrogen is by itself, but hydrogen, we can't write it by itself. It's going to be H2. Okay? Now, this is something you need to remember for the AP exam. We'll go over this a few more times as we're reviewing for it. When you add a metal to hydrochloric acid, then you're going to make hydrogen gas. Okay? You guys remember doing this? We actually did this in the gas. You remember those thin gas tubes? Okay? You put magnesium metal down at the bottom of the hydrochloric acid and the hydrogen gas came up. Okay? So just keep that in mind. That's a really good thing to remember because they'll ask this type of question a lot. Here's the problem. This is aqueous, this is solid. Magnesium chloride is soluble in water, okay? And you have to kind of know your solubility rules on that one. And this is a gas. So this is not our net ionic equation here because there's something that does nothing in this equation. What is it? The chlorine is aqueous or aqueous on both sides, right? So remember, on number 4 on the AP exam, you have to write the net ionic, okay? So the net ionic for this one is going to look like this. Mg solid plus H plus. Actually, we got to balance this thing, don't we? Just a 2 there, so 2H plus. Yields Mg2 plus H2. Okay? There's your net ionic equation. Now, the nice thing about the net ionic equation is it's much easier to see the oxidation-reduction half reactions occurring there. Okay? The magnesium starts out with a 0 oxidation state, it goes to a 2 plus. The hydrogen starts out with a 1 plus and it goes to a 0. Does everybody see that? Okay? So, if I'm going to write my oxidation half reaction, what's that going to be? Okay, the Mg solid going to Mg2 plus, that's the oxidation because it's becoming more positive, so it must be losing electrons. Okay? And then our reduction half reaction would obviously have to be the other one. 2H plus going to H2. Okay? Does everyone feel like you could come up with that on your own? The equation writing is sometimes the hardest part of, well, I don't know if there's a lot of hard parts on the free response, but that's one of the hard parts for students because it requires so much understanding of what's going to happen in a chemical reaction, and that's tough. Okay, sorry that one took a while. We'll see you in class.